Hey YouTube, it's Dimitri, and today we're going to talk a little bit about the mechanics behind how we actually do the splitting and how we do the predictions here inside of a decision tree. More specifically, today we are going to do categorical decision trees here. So let's just write this on the screen. So this is going to be categorical. What this means is that your dependent variable here, so in data science terms, they typically call this the target variable. This is what we're going to be predicting here, is categorical in the sense that it just takes on very specific values. So for our case today, we're going to do PD again, which is the probability of default. You can look at customers over some sort of time frame, say, I don't know, 2-year period, lifetime, something, and say, did this customer default? If they defaulted, then they're going to get a value of 1. If no default, then they're going to get a value of 0 here. So we're modeling a categorical problem here. An example, though, if you were doing a continuous variable here, so continuous would be something like income, right? Because income can range from like 0 to, I'll just say, infinity, and it can be in dollars and decimals, which is pretty granular here. And so in this case, this would be a regression problem. But today we are not doing regression. Today we are going to be doing a categorical decision tree. And so just to start off with here, there's kind of 2 things I'm going to talk about. One is going to be, you can call it an algorithm. I'm just going to call it math. That's what we're doing. We're doing some math. So what is the math that we need to do to split the tree? So, all right, so you should have some sort of tree. This is what's called the root. And then you do some sort of splits, and you have, more kind of splits here, branches, as they typically call them. And then finally here, after you have all your splits, you have what are called leaves. And so the leaves are going to be the final prediction here. And so I'm going to answer the second question actually first, and we'll probably come back to this here at the end a little bit. But what is the prediction for a leaf? And in our example here, it's just going to be an average here. So what we're going to do is we're going to take a bunch of data. We're going to split it all up based on a bunch of rules. We're going to end up with these leaves down here. And each leaf is just going to be the average. So this is going to be the average value. We'll just call it of X. And X is going to be filtered based off this tree such that you come down this path and up here. Again, this one is going to be the average of X, where the X's have been filtered. So these variables have been filtered all the way down into this leaf here. So all it is going to be an average here. And we'll talk a little bit about this at the end here. But let's just dive on into the math so we can quickly go through kind of the mechanics of it. I know many of you are going to think this is boring. Understanding, though, how the mechanics and the math actually works. And no, we never do this in practice because you'll see here we have I think I have 6 or 8 data points here, and it takes me quite a long time to do it by hand. You're going to need a computer. But understanding these mechanics is going to show you theoretically, as I've kind of mentioned, the probability theory and the measure space kind of coming together. So measure theory here a little bit. How are we getting to all these other conclusions? So I'm going to show you why the trees are failing, why you shouldn't use them in specific scenarios here in future videos. And as I explain these sorts of things, you need to understand the mechanics here to understand and draw these sorts of conclusions. Because not surprising, I haven't seen a lot of this in textbooks. So I read a handful of machine learning books here and there. I don't dive a lot into them. But often I see people that say, "Oh, Dimitri, how did you come up with this conclusion?" And it's just diving into the math and figuring out how it actually works, and then obviously seeing if it works this way, this is a potential issue. Okay, so let's start off with our data here. We're gonna have default, and we're gonna have, this is what we're modeling. This is our dependent variable, and we have 0, 0, 1, 0, 1, 1. So if you think about this like an index inside of Python or some sort of customer ID, you have 1, 2, 3, 4, 5, and 6. So we only have 6 data points. As I go through this now, just imagine doing this by hand on like 1,000 data points. It gets pretty crazy. So computers are absolutely amazing, which is why we love using a computer here. We're going to have LTV here. So LTV, again, for those of you that don't know, in the finance world, this is loan to value. So if a vehicle's valuation, say it's worth $10,000, and you get a loan for $10,000, LTV is 1. Now, if you were buying, say, a $10,000 car and let's say you put $5,000 down on the car, and so you only needed a loan for $5,000, but the car is worth $10,000. Your LTV is 0.5. It's very safe because if you default, the bank or financial institution can sell the car hopefully for $10,000, collect the remainder of the balance they owe you, which the maximum is going to be $5,000 here, and can be made whole. Now, there are scenarios where a car, let's say it's a used car, 15 years old, it's only worth, $1,000. But a dealer's, for some reason, selling this car for like $1,500. Now you have a 1.5 LTV. So you can see here that, as LTV is high, this is high risk. And as LTV is low, we have low risk. Just trying to give you guys a little bit of the finance intuition here. But we have LTV here going to be 0.35. So 0.35, 0.52. Let me just fill these in real quick. Okay, so in practice here, this would be like the data set that you get. You don't just make this data up like I'm doing, but you would get a data set and this is what it would look like here. Now, when we start to go into categorical here, what we're going to do is we're going to look at our independent variable. So LTV is going to be our independent. And what this means is that independent variables are what are driving or calculating our prediction to predict the dependent variable. So that thing that we're predicting is dependent on these independent variables here. And you could have multiples. Today, we're just going to do univariate. And what I mean by this is we're just using one variable. You could do multivariate where you could have, 2, 3, 4, 5, 6 variables. All the math still works the same. But we have our independent variable here. And what we're going to need to do is figure out, answer the question, where do we split this tree at, right? And to answer this question, let's just look at our data here quickly and say, okay, we have some duplicates, right? So 0.88 is a duplicate. Those are duplicates. So we're probably going to keep all those in the same bins. And what we're going to look at is how would we split this up just based on the differences in the data here. So you can see, okay, 0.35 and 0.52, we could potentially do a split here. Again, 5.2, 5.2, can't divide those up, but we could split 5.2 and 8.8. And then you could split out 0.88 and 1.05. So hypothetically, right, this could be 1 group, 2, 3, and 4. So I'm just going to call these groups for now. And what we're going to do is we're just going to go through here and calculate these out such that we have one split where we take the data and we split it and say, okay, if LTV is less than or equal to, and we'll have some value here, which I'll give you in a second, then this is going to be one split. And this would be group 1, and then this would be groups 2, 3, and 4. And this is going to be groups 1 and 2, right? Because now we're splitting out this piece versus this piece. So we're going to have 1 and 2, and then we're going to have 3 and 4 on this side. And then finally here, what we're going to have is we're going to have LTV less than or greater to some value. And we're going to have 1, 2, and 3. And then we're going to have group 4 here, right? So in our scenario, those are all the possible splits, right? You could have 1 versus 1 to 3. We could have 2 versus 2, as I showed before. And then we could have 1 to 3 versus 4 here. Now, if you had a lot of data and a lot of granularity, right, there are infinitely number of splits you can do here. So it starts to get complicated as the data kind of blows up. All right, so let's figure out how we're going to get these values, right? What is the split here? So when I'm talking about X, like right here, what is that X going to be? What we're going to do for simplicity on this is we're just going to take the average right here between these two groups. So in this case, we're just going to do 0.35, which is the first number, plus 0.52, which is the second group split. And we're going to divide them by 2 to get the average here. And this is going to give us 0.435. And that is what's going to go here. So this will be 0.435. And then to get this second split here, what we're going to do is 0.52 plus 0.88 divided by 2. So get the average of that point. And we're going to get 0.70. And then finally, to get the split between 3 and 4, we're going to get 0.88 plus 1.05 divided by 2. And that's going to give us 0.965. Okay, so that's just how we do the splits, right? We have to figure out how to split it. We don't really have granular enough data between those points. We have these kind of groups here that we're going to test out and figure out which split is going to be the best split. Okay, so to do the actual math here, let's just go through this step by step. First, we're going to test out, we're going to call it 1 versus 2, 3, and 4. And so what we're going to do is say, okay, if LTV is less than or equal to 0.435, this is my proposal here. We need to go to the left here and say, okay, if this is true, so this is group 1. How many of the dependent variable ones do we have and how many of the zeros do we have here? And what we're trying to do is figure out how do we get a nice clean split so that they're very pure. Meaning if we follow these rules, we don't have any variance, we have a perfect prediction, right? We're trying to maximize that perfection of prediction here. We'll never get there. We'll get to that in another video of theory. But all we're gonna do is go through and look at this. So we look at group 1 up here, and right, there's only one data point there that's going to meet this rule, which is gonna be less than 4.35. And our target variable here being default is going to be 0. So we have 0 ones and 1 0. Okay, so I'm going to put this here as a box. And then this other piece here, the other side we're going to test to this rule is anything greater than an LTV of 0.435. And if you look again here on this column right here, we can count and say, okay, how many ones do we have? Well, we have 1, 2, 3. So we'll put 3 here. And then how many zeros do we have? We have 1, 2. So we're going to put 2 here. And then I'm going to put over here, this is called the Gini impurity. And this is going to be for the leaf. I'll show you how we weight this to do the entire split altogether. You can use other metrics too. There are other things like entropy you can use for this. It's measuring almost the same thing, right? We're trying to figure out how good is the split, how pure are each of the leaves. And so we're going to have this equation of 1 minus the probability of the event, which is 1 occurring squared, minus the probability of 0, the event not occurring squared. And so in our example here, what we're going to do is we're going to say, okay, 1 minus our probability of 1 occurring. So we're going to do this first leaf here. So this is leaf 1. We have, 0 1 events, and there's a total of 1 observation here in this leaf. So we're going to square that. And then we're going to minus the total of 0 events. So there's only one of these events that have the value 0. So it's going to be 1 over 1. That's going to be squared. And then this is just going to be equal to 1 minus 0 minus 1. And this is going to be equal to 0. So what this is telling you when the Gini is 0 is that we have perfect purity. So if we made this split, this leaf is 100% pure, right? We have only one type of value in here. Now we want to do the right side split here, which is going to be 2, 3, and 4, right? And so to do the 2, 3, and 4, what we're going to do is the same equation here, and we're going to say, okay, 1 minus, and we're going to say, okay, how many 1 events do we have? We have 3 right here, so we're going to have 3 over. How many total observations do we have? 3 plus 2 is going to be equal to 5. So we're going to square that, and then minus the zeros. So how many non-events do we have? We have 2. And again, there's still 5 total observations in this leaf. We're going to square that, and that's going to give us 1 minus 0.36 minus 0.16, and this is going to give us 0.48. Now that's great, but we still have 2 leaves, and so we have this split, and we have a left leaf and a right leaf. So how do we, reconcile the fact that there's different number of observations in each leaf? We are just going to take the weighted average of the 2 leaves, and this will give us, so this will be equal to our split Gini. So I'm going to call that here. And so in our case here, what we're saying is, okay, in this one group here, right, there's only 1 observation. So this is going to be 1 over 6. And that's going to be multiplied by, again, our Gini of that leaf. And that is going to be 0. So this is going to be times 0 plus this other group of leaves here. Again, there are 5 observations in this leaf, and there are a total population of everything is going to be 6. So we're going to have 5 from this right leaf divided by 6. And then we're going to multiply that by 0.48, which was our leaf Gini, and that'll go here. And then this will give you 0.40. So I'm going to make a little note here and just put 0.40. So that's what this split is generating for the Gini. Okay, so next we're going to test LTV less than or equal to 0.70. So this is the second split where you have groups 1 and 2 versus groups 3 and 4. And so we're going to calculate this one out. So this is 1 and 2. And again, we're going to have 1 and 0. And so again, we look in 1 and 2, how many ones do we have? Right, in this side, we have 1. How many zeros? We have 2. So we'll put a box around that. And then let's just do the Gini calculation real quick. So 1 minus the probability of the event occurring. There is 1 right here. So 1 over total in this leaf is 3. We're going to square that. And then we're going to minus the events of no event is 2. Again, total 3 events in this leaf. Squared, this is going to be equal to 1 minus point, so 0.11 minus 0.447. And this is going to give us 0.443. And then we're going to do our right side split here. So this is groups 3 and 4. How many ones? How many zeros? So again, how many ones and zeros now on this side? There are 2 ones and 1 0. So now to do the Gini calculation here, we have 1 minus, again, 2 out of a total of 3 in this leaf. And that's going to be squared, minus 1 divided by, again, the total of 3 in this group, squared. And this is going to be equal to 1 minus 0.447 minus 0.11. And this is going to give us 0.443. I will note here, out of interest, out of mathematics, and things I think are interesting, right? We have the same value on the left leaf as the right leaf. That's because we have the same ratios. We have 1/3 of an event, which makes it, 2/3 non-event, to again, 2/3 of an event to 1/3 non-event. So even when you have an inverse flip here, again, the purity of those leaves is going to be the exact same. But again, one leaf predicts more defaults, one leaf predicts less defaults. And then now I hope you guys can figure this out real quick. The weighted average of 2 numbers that are the same is just the numbers themselves. But out of mathematical, completeness, which I really enjoy and like in videos, we're going to do this weighted average here. And this is going to be 3 out of 6. Right, so there are 3 values, data points in the left leaf. There are 6 in total out of the whole data set here. And then we're going to times that by that left leaf with the 0.443. And then we're going to add that to 3/6, which again, there are 3 data points in the right leaf. There are a total of 6 data points in all the leaves in this split. Again, times 0.443. And of course, this will give us 0.443. Okay, and in our final split here, we're going to do this last one. So LTV is less than or equal to 0.965. And again, this is going to be now groups 1, 2, and 3. This is going to be over here, groups 4. And now let's count our 1s and our 0s. So again, our split is going to be this wonky one right here. And if we count above this line, how many 1s do we have? We have 1, 2. How many 0s? 1, 2, 3. Now again, to do the Gini, we're going to do 1 minus, and then how many of the events do we have? We have 2. How many are in total in the leaf? There are 5. We're going to square that. Minus non-events, which is 3 over a total of 5 in that leaf. And that's squared. And then this is going to give us 1 minus 0.16 minus 0.36. And this is going to give us 0.48. And then we'll do this side. So 1s, 0s. In group 4, there's only 1 data point here. It is a 1. So, right, this is just a 1. There's 1 here and 0 here. And so we're going to calculate the Gini again for this proposed leaf. And this is going to be 1 minus 1 over 1. So there's 1 event. There's only 1 data point squared minus 0 over 1. No non-events squared. And then this is going to be 1 minus 0. And this is going to be equal to 0 again. And this is 100% purity. And that's, you don't need to know that. I'm just trying to add some intuition on that's what that means, right? There's no impurities. It's all just one value. And then if we do a weighted average of this, there are 5 data points in the left leaf. So 5, there are a total of 6 in our data set here. where we're considering this split. So if you're splitting down through multiple leaves, you won't use the entire data set here because we're starting to partition out. But in our full set of the 2 leaves, more importantly, this is the 2 leaves total. Anyways, so that's the weight times 0.48, and then plus our right leaf is going to be 1 value. The leaf split we're considering, the total of these 2 leaves is 6, and we're going to times that by 0. So this will give you 0.40. So we'll put it right here, 0.40. Okay, so now what we're going to do is we're going to say, okay, we have 3 options of splits, right? We had this one, we had this one, and we had this one. We would pick whichever one is the lowest split. Well, in this case, there are actually 2. So you could pick either one. Probably in a computer programming language, we'll probably pick the first one that appears. So what we would technically do is build this tree and say LTV is less than or equal to 0.435. And then again, this would be group 1. And this would be the leaf. And then this would be groups 2, 3, and 4. Now in practice, right, we cannot split group 1 anymore because there's only 1 data point inside of there. But in the right side, 2, 3, and 4, we still have 5 data points. You could again split this again now and try the other groupings. So you might end up splitting, just hypothetically, you might have a split where its LTV is less than or equal to 0.965, for example. And then you might have a leaf here and another leaf here. Or if you stuck with our example, you would just basically have 2 leaves, right? So this would be 1 leaf, and then this would be the second leaf. But as I mentioned, right, you can split up because you have 5 data points in here. You can keep splitting these things up. And also categorically based on LTV, you know, we have areas to split because we have differences in data. Once you hit purity, you can't split anymore. So purity and data points restrict you from splitting so far. This is a theory piece we're going to talk about later with overfitting and decision trees. But for this example, now we're going to calculate what is the prediction of leaf 1. Again, right, I told you this is the average of all the data points in that leaf. So in group 1 up here, we only have 1 data point and it's only the value of 0. So what you would do is say 0 divided by 1 data point, and this will give you a prediction of 0, right? So any value that is going to be less, the LTV is less than or equal to 0.435, this is going to be equal to 0. So that's what the decision tree predicts. Doesn't matter if your LTV is 0.35, as in our case, 0.1, 0.4, the prediction this tree is going to generate is going to be 0. Then in the right-hand side here, it's a little more interesting here. It's going to be 0 plus 1 plus 0 plus 1 plus 1. And then we're going to divide that by 5. So we're just taking an average here. You add them all up, divide by n. So there's 5 of these. And this is going to be 0.6. So what this is saying, right, is we're not saying it's 0 and 1, right? We're predicting the probability of an event occurring. So in this case, any value that is greater than 0.435 here, so it could be, you know, 0.88, 0.9, I don't know, 0.51759, I don't know, something crazy. The prediction for all of those is going to be 0.16. And so this tree is going to just do 2 predictions. You either go left and you get a prediction value of 0, or you go right and you get a prediction value of 0.6. All right, so now to dig in this a little bit deeper here at the end, I'm going to ask you guys a question. I want you to think a little bit about it here. And the question is going to be, why not use other predictive metrics such as median and mode? So the answer to this is you can do anything you want technically in those in leaves, right? It's just math, right? We're just doing math. You could have had the decision tree we had, and instead of taking the average value, we could have taken the median. This is just another example here. Or you could have taken the mode. Or you could get creative and you could do something else. But you would need to use that consistency across all the leaves so they're comparable. The question, though, is like, why and when would you do this? Well, it depends on your data. So it depends on understanding the population of your data set and how representative it is. Again, it has to do with your sampling theory. So how representative is the sample of the population? Are you missing pockets? Do you know you're missing pockets? Do you know there's a bias in the data? Again, if you remember, like you have this nice bell curve, right? The mean and the median and the mode can all line up sometimes. Okay, so in that case, it won't matter. But if you have like a skewed distribution, there might be an advantage to actually getting, again, the peak here. And getting this peak here, again, might be the median. And the mode and the average value, so the mean, might be sitting over here. And so depending on your problem, you're going to have different values. But again, to answer this, there's not a simple thing like if this, then that. This goes down now into what I was talking about before, which is you can't just learn to fit trees and then blindly fit trees, guys. You got to start thinking about these theories. And when I said you need to take probability and measure theory and people started losing their minds, this is why. Because when you start to build complex models with millions or billions or even trillions of dollars if you're in the mortgage markets and you're proposing some sort of decision tree here, you better understand your data. You better understand, again, the population, the sampling. I'm going to talk about all this in much greater detail in the next video or maybe a couple videos out. But you need to understand the space that you're operating in and how well you're covering that space so you can figure out, you know, if there's going to be issues or potential issues, and I'm going to talk about that. But again, looking again at the distribution. So this distribution now is coming from your sample. Is your sample, again, representative of the population? No, you can't just say, oh, I have 100 data points randomly sampled and therefore it's representative. This is complete nonsense. These are the things I worry about because I have actual dollars on the line in the quant finance space here. This isn't just a fun academic-y thing to do here. So again, I'm hoping you guys look at this chart, look at my diagrams, think about how the math churned through to get to these predictions here, and start to think in your head, how does overfitting occur and why does it occur? How would you prevent it? Again, should you even use the standard, which is the average of each leaf? Should you use the median, the mode? Should you use something different? Should you come up with some crazy metric to put in there to get these sort of predictions, right? Again, you might look at variance, for example, within these leaves. There's a whole bunch of cool things you can do about that, but please start thinking about this because we're going to start covering this in future videos here. And I'm hoping you guys can see here on the quantitative finance side, what really differentiates us and what I think is failing both in the quant finance side and in the data science side is we don't have enough of this depth in the mathematics to really kind of pull apart the models and figure out like, this is the most amazing opportunity for a decision tree. That is why I chose that versus somebody's using a decision tree for this. And this is scary because it is not the appropriate tool to be using for this problem here. So anyways, thanks for listening. Thanks for watching. And as always, until next time.